Welcome to today's paper reading. Today's paper is titled, Rethinking Data Augmentation for Robust LiDAR Semantic Segmentation in Adverse Weather. This paper was published on AR14 by Junsung Park and colleagues from KAIST and Yonsei University. The abstract highlights the challenges faced by existing LiDAR semantic segmentation methods in adverse weather conditions. Previous approaches have attempted to address these issues through weather simulation and data augmentation, but they lack a detailed understanding of how adverse weather affects performance. The authors identified two main causes of performance degradation: geometric perturbation due to refraction and point drop due to energy absorption and occlusions. To address these issues, the authors proposed two new data augmentation techniques: selective jittering, SJ, to mimic geometric perturbation, and learnable point drop, LPD, to simulate point drop using a deep Q-learning network. Experimental results show that these techniques significantly enhance the robustness of LiDAR semantic segmentation models, achieving a 39.5 MIU on the semantic kitty to semantic STF benchmark and improving the baseline by 8.1% P, establishing a new state-of-the-art. LiDAR semantic segmentation is crucial for 3D scene understanding, especially in autonomous driving and other safety-critical applications. However, existing models often show significant performance degradation under adverse weather conditions such as snow, fog, rain, and wet surfaces. To address this, we adopt a data-centric approach to analyze corrupted LiDAR data, identifying two main distortion types: geometric perturbation and point drop. This approach aims to improve model robustness without relying on precise weather simulations. In the field of 3D LiDAR point cloud semantic segmentation, methods can be broadly categorized into three types based on their data representation. Point-based methods, such as KPCONV and Point Transformer, directly utilize the 3D points as input, with KPCONV clustering local points and Point Transformer using k-nearest neighbors. Projection-based methods, including RangeVT and RangeFormer, project LiDAR points into a 2D image format, leveraging models like FIT and techniques like RangeAugust. Voxel-based methods, such as Minkowski-Net and Cylinder 3D, divide the 3D space into a voxel grid, with Minkowski-Net applying sparse convolution and Cylinder 3D using cylindrical partitions to reflect LiDAR's point density characteristics. In this section, we discuss the common distortion patterns in LiDAR data caused by adverse weather conditions. The first type of distortion is point drop, which occurs due to beam attenuation and beam missing caused by droplets, fog, and wet ground. The second type is occlusions, where beams colliding with snow collect signals at shorter distances than intended, leading to occlusions in adverse weather. The third type is geometric perturbation, where random noise is added to the coordinates of LiDAR points, affecting data in conditions like fog, snow, and rain. The fourth type of distortion is intensity distortion, where adverse weather conditions like fog, wetness, and rain lead to a reduction in LiDAR beam intensity, affecting the generation of synthetic data. To understand these distortions better, we conducted a toy experiment using synthetic data generated from the semantic kitty validation set and the Minkowski-Net model. The results showed significant performance degradation with increasing distortion in D1, D2, and D3, while D4 maintained performance levels despite significant distortion. Figure 1 provides a visualization of the results from the toy experiment. The figure highlights that green points represent correct predictions, while red points indicate incorrect predictions. The primary distortions causing performance degradation are identified as point drop, occlusion, and geometric perturbation. Notably, the areas of misprediction for point drop and occlusion largely overlap, suggesting they could be considered as the same type of distortion. This visualization aids in understanding the impact of these distortions on the model's performance. Table 1 presents the results of toy experiments conducted on the validation set of semantic kitty. The table categorizes the distortions into four types: point drop, D1, occlusions, D2, geometric perturbation, D3, and intensity distortion, D4. Each distortion type is applied at two severity levels, soft and hard. The results indicate a significant performance drop as the severity of D1, D2, and D3 distortions increases, with performance falling below half of the baseline. In contrast, D4 maintains relatively stable performance even under significant distortion. Notably, the performance drop in D2 is argued to be similar to D1, attributed to the alteration of the local geometric structure due to occlusions, which has an effect akin to point drop. This similarity is further evidenced in Figure 1. To enhance the robustness of the model, the authors propose two main techniques: selective jittering and learnable point drop. Selective jittering includes depth selective jittering, DSJ, angle selective jittering, ASJ, and range jittering, RJ. These methods add Gaussian noise to points to simulate geometric perturbations. Learnable point drop, LPD, uses a deep Q-learning network, DQN, to identify and simulate point drops due to occlusion. The overall pipeline involves data augmentation through selective jittering, followed by loss and entropy calculations, and reward computation for the LPD module to train the model effectively under adverse weather conditions. Figure 2 illustrates the learnable point drop, LPD, mechanism, which is crucial for enhancing the robustness of LiDAR semantic segmentation models against adverse weather conditions. The process begins with LPD utilizing the loss, log, and entropy, HAUG, derived from the LiDAR segmentation model as its current state. Upon receiving a point input, LPD performs a point drop and then recalculates the loss, LLPD, and entropy, HLPD. The difference between these new values and the previous ones is used to compute the reward, which guides the model's learning process to make accurate predictions even in the absence of critical points. This mechanism ensures that the model can effectively learn to handle point drops caused by adverse weather conditions, thereby improving its overall performance and reliability. Figure 3 illustrates the comprehensive training process for the learnable point drop, LPD module. Initially, selective jittering, SJ, is applied to the data. Following this, the loss is calculated, which leads to the update of the LPD state. This process is then followed by utilizing the LPD to generate dropped points. Subsequently, the loss is recalculated, and the reward is updated accordingly. This iterative process enables the LiDAR semantic segmentation model to effectively learn points distorted due to adverse weather conditions. In this section, we will discuss the datasets used for our experiments, including Semantic Kitty, Semantic STF, and SynLiDAR. We evaluated our model's performance using metrics such as intersection over union, IOU, for each class and the mean IOU and MIOU across all classes, considering various weather conditions. The implementation details include using Minkowski-Net 18/32 width as the baseline model, with a learning rate of 0.24 and a batch size of 2. These experiments were conducted over 15 epochs using 4A6000 GPUs. Figure 4 presents the qualitative results of our method from the validation set of Semantic STF. All models were trained using the trained set of Semantic Kitty. The figure uses green points to indicate correct predictions and red points for incorrect predictions, demonstrating that our predictions are more accurate than those of point DR across all weather conditions. This accuracy is especially notable on road and sidewalk surfaces. Figure 5 presents the qualitative results of the LPD, local point dropout, method applied to the validation set of Semantic Kitty. The figure illustrates that the point drop facilitated by LPD is not confined to local areas but is distributed across all points. This characteristic effectively mimics the occlusions and sparse point distributions typically observed in real adverse weather conditions. However, it is important to note that LPD does not replicate the specific effect of wet ground surfaces, which is a limitation highlighted in the study. This limitation suggests the need for further development of methods to address this issue, ensuring a more comprehensive representation of adverse weather effects in the model. Table 2 presents the LiDAR segmentation results measured by mean intersection over union, MIOU, on the Semantic STF validation set. The table is divided into two sections: A. Models trained with Semantic Kitty, and B. Models trained with SynLiDAR. Key findings include significant MIOU improvements in adverse weather conditions such as rain, snow, and fog. The baseline plus SJ plus LPD method demonstrates superior performance across all weather conditions, outperforming recent competitors like PointDR. Notably, the method achieves the most significant MIU increase in rain, indicating the effectiveness of the SJ augmentation in modeling geometric perturbations caused by raindrops. This table underscores the robustness of the proposed method in enhancing LiDAR semantic segmentation under various weather conditions. Table 3 presents the experimental results of various components of our methods using Semantic Kitty as the source and Semantic STF as the target. The table highlights the performance improvements or decreases over the baseline model, indicated in parentheses. The addition of ASJ, adaptive selective jittering, significantly enhances robustness across all adverse weather conditions, with increases ranging from plus 2.6 MIU in dense fog to plus 8.1 MIU in rain. The introduction of DSJ, dual selective jittering, further boosts performance in dense fog, light fog, rain, and snow, with improvements ranging from plus 4.1 MIU to plus 9.3 MIU. Lastly, the application of LPD, LiDAR point dropout, demonstrates substantial enhancements in dense and light fog conditions, indicating its effectiveness in representing occlusion from foggy weather. Table 4 presents the LiDAR segmentation results measured by mean intersection over union, MIU, across different architectures and datasets. All models were trained using the Semantic Kitty dataset. The table highlights the performance improvements achieved by incorporating our proposed method. Specifically, for the Semantic STF dataset, our method increases the MIU of SENET by plus 7.8, SBVCNN by plus 10.3, and Minkowski-net by plus 8.1 MIU. These improvements demonstrate the effectiveness of our approach in enhancing the robustness and generalizability of LiDAR semantic segmentation models. The study focused on analyzing distortions in LiDAR data caused by adverse weather conditions and enhancing the robustness of LiDAR models using a data-centric approach. Through experiments, it was identified that point drop and geometric distortions significantly affect model performance. To address these issues, novel data augmentation techniques, including selective jittering and learnable point drop, were introduced. These techniques led to state-of-the-art performance on the Semantic STF dataset. The methodology significantly contributes to enhancing robustness without the need for complex data simulations. The research is expected to improve the stability and reliability of LiDAR semantic segmentation. Thank you for watching.